This is a production of the Chemical Education Material Study. Here are 2 beakers of ordinary tea. You may have observed, when lemon juice is added, a color change occurs. Likewise, vinegar affects red cabbage. Here is red cabbage juice plus vinegar. Hydrochloric acid changes the color of litmus paper. So does lemon juice, as does vinegar. All 3 are acids. The dyes in tea, cabbage, and litmus change color when acids are added.
So chemists have developed a large set of substances whose colors change as acidity changes. Such substances are called acid-base indicators. How do they work? We'll start with bromethymol blue.
Here are 3 beakers containing pure distilled water. Pure water is said to be neutral. In a neutral solution, the concentration of aqueous hydrogen ions equals the concentration of hydroxide ions.
The symbol H3O+ represents aqueous hydrogen ions, also called hydronium ions. Their concentration is 10 to the minus 7 moles per liter at room temperature. They may also be identified as H+ aqueous, or more simply, as hydrogen ions or protons.
Now we'll add some gaseous hydrogen chloride to this beaker of neutral water. The hydrogen chloride reacts with water, producing hydronium ion and aqueous chloride ion. The hydronium ion concentration increases. The hydroxide ion concentration decreases. Acidic solutions are those in which the hydronium ion concentration is greater than the hydroxide ion concentration. Next, we'll add solid sodium hydroxide to one of the other beakers of neutral water. The concentration of hydroxide ions increases. The solution becomes basic. Basic solutions have a lesser concentration of hydronium ions than hydroxide ions. Now let's add some of the indicator bromethymol blue to our solutions. We see that the indicator is yellow in the acidic solution. The indicator is blue in the basic solution and an intermediate color in neutral water. If we evaporate the blue solution, we obtain this solid. This solid is obtained by evaporating the yellow acidic solution.
Why did the indicator change color in these solutions? Analysis of the blue substance shows its color is due to blue negative ions with this structure. Analysis of the yellow substance shows that its color is due to yellow molecules with this structure. The only difference between the yellow form and the blue form is the presence of a proton here in the yellow form. This proton would be missing in the blue form. Addition of a base, such as hydroxide ion, allows the yellow substance to donate this proton to form water and the blue substance. Conversely, acceptance of a proton by the blue substance gives the yellow one. Indicators such as bromethymol blue can undergo acid-base reactions, changing color as they donate and accept protons.
We can simplify our representation by letting H stand for the acidic proton and BB for the rest of the bromethymol blue. Thus, HBB represents the yellow form, and BB minus the blue form of the indicator. Acting as an acid, bromethymol blue donates a proton to a base like hydroxide ion, giving water and the blue basic form. Similarly, the blue form, acting as a base, can accept a proton to give the yellow form again. If we consider only loss and gain of a proton by the indicator, we get these simpler equations. We can combine these to give a single equation showing proton transfer to and from the bromethymol blue. Thus, all acid-base indicators are substances which can donate and accept protons, with resulting color changes. We have accounted for the yellow and blue colors, but what about the color found in the neutral water? Here, arranged in Petri dishes, is a set of solutions to which bromethymol blue has been added. The colors change gradually from yellow to blue. Actually, there are two sets of dishes. All of one set are yellow, all the others blue. The solutions in the yellow dishes are all equally acidic. They contain mainly yellow HBB. The solutions in the blue row are all equally basic. They contain mainly blue BB minus. The number of drops of indicator added to each dish is shown. A total of 10 drops has been added to each pair of dishes, although the ratio of blue to yellow ions varies. Now we observe that the color in the overlapping central dishes corresponds to the color in our beaker of neutral water containing bromethymol blue indicator. The solution in the beaker has the same color as that caused by equal amounts of yellow and blue. Whenever equal concentrations of the yellow and blue forms are present, the intermediate color is produced.
The intermediate color can give useful information concerning the acid strength of the indicator. Acid strength can be measured quantitatively by measuring the equilibrium constant, K. Let's determine the equilibrium constant for bromethymol blue acting as an acid. We start with a chemical equation. To evaluate K, the concentration of the products is placed in the numerator. The concentration of hydronium ion is multiplied by the concentration of BB minus, the blue form of the indicator. The reactants go in the denominator. The concentration of water does not vary appreciably, so we can combine its constant value with a constant K to give us a new constant, KHBB, the ionization constant of bromethymol blue. In the water solution, the concentrations of the blue and yellow forms are equal. Since these concentrations are equal, they cancel, and the ionization constant equals the hydronium ion concentration in the neutral water. Thus, KHBB equals the concentration of H3O+ in neutral water, which in turn equals 10 to the minus 7. KHBB, therefore, is about 10 to the minus 7. Are there other indicators which behave similarly? We'll try methyl orange. Small amounts of methyl orange are added to solutions containing the hydronium ion concentrations shown above each dish. After each solution has been stirred, the indicator is red in the highly acidic dish. When the hydronium ion concentration equals 10 to the minus 4 moles per liter, the solution color is intermediate. From 10 to the minus 5 on, the indicator is yellow.
We use the symbol HMO to represent the red substance. It is an acid which begins to donate protons noticeably in the second dish, when the hydronium ion concentration is about 10 to the minus 4th molar. The H plus again stands for the proton which has been donated, and the MO minus stands for the balance of the methyl orange molecule. The red form can donate a proton, leaving a yellow form. The aqueous hydrogen ions, represented by H plus, are colorless. The equilibrium constant is expressed in the usual way. The intermediate orange-colored solution must have about equal concentrations of the red and yellow forms of the indicator methyl orange. Therefore, in the orange solution, these concentrations are equal. Since the hydronium ion concentration is about 10 to the minus 4th molar, it follows that the ionization constant for methyl orange in water is also 10 to the minus 4th. We showed that the equilibrium constant of bromothiamyl blue is 10 to the minus 7th. Methyl orange, with an equilibrium constant of 10 to the minus 4, must be a stronger acid than bromothiamyl blue, and BB minus must be a stronger base than MO minus. Next, let's test methyl red. The intermediate color appears at 10 to the minus 5th molar hydrogen ion concentration. The acid, methyl red, therefore, has an ionization constant of about 10 to the minus 5. Methyl red is a weaker acid than methyl orange, but stronger than bromothiamyl blue. Here is still another indicator, phenolphthalein. As we add this indicator to solutions of varying acidity, we see that it is colorless until the hydronium ion concentration is about 10 to the minus 9 molar, where the phenolphthalein becomes colored. Therefore, the ionization constant of phenolphthalein is about 10 to the minus 9.
Now that we know the ionization constants of several acid-base indicators, let's consider some uses of our knowledge. You may have used a universal indicator on paper. How can we prepare such an indicator? Here we compare our tested indicators. The strongest acid, HMO, is at the top of the left column, and the strongest base, PTH-, is at the bottom of the right column. Thus, the strongest acid is methyl orange. Next comes methyl red, then bromothiamyl blue, and phenolphthalein. Let's experiment further with the acid strengths of the indicators. Here are our 4 indicators. Each horizontal row shows the color of one of the 4 indicators as the acidity varies from 10 to the minus 3 to 10 to the minus 9 moles per liter. Each vertical column contains solutions of identical concentration of aqueous hydrogen ion. Each indicator donates protons and changes color at a different acidity. Methyl orange donates protons appreciably at 10 to the minus 4, methyl red at 10 to the minus 5, bromothiamyl blue at 10 to the minus 7, and phenolphthalein at 10 to the minus 9. Each is a weaker acid than the ones above it. Now, let's superimpose the dishes. Each vertical stack contains the same total amount of indicators and the same hydrogen ion concentration. Each stack shows a different color, since the ratios of acid to base forms differ. We can now proceed to synthesize a universal indicator. Our universal indicator will consist of a single solution containing all 4 indicators. Let's try it.
A beaker of water is placed on a magnetic stirrer and some of our universal indicator is added. The hydrogen ion concentration in water is about 10 to the minus 7th molar. So in this mixture, the phenolphthalein is colorless, the bromethioblue is partly blue and partly yellow, and the other indicators are yellow, giving this total color. From a burette above the beaker, we first add acid. The blue form of the bromethioblue accepts protons from the added acid and becomes yellow. As we add more acid, the methyl red molecules accept protons, forming red ions. These are mixed with all the other yellow forms and give orange as a total color. Next, with still higher acid, the methyl orange also accepts protons, and the solution turns red. These 4 indicators have, one after another, now accepted protons. Let's stop adding acid and add base to the indicator solution. The strongest acid, methyl orange, donates protons first. The solution is again orange. Next, the methyl red donates protons, leaving only yellow forms in solution. Each indicator changes color over a narrow acidity range. The range depends on the acid strength of the indicator. Continued addition of base allows the weaker acid, HBB, to donate protons. Finally, the phenolphthalein donates protons as the hydrogen ion drops to about 10 to the minus 9th molar, and the solution turns violet.
Analysis shows that the color changes in tea and cabbage juice are similar, also due to sets of complex acid-base indicators. In the laboratory, to test for acidity, we used pure substances of known composition. All these indicators, even the complex universal indicators, are acids and bases which can donate and accept protons, changing color as they do so at particular hydrogen ion concentrations characteristic of their acid strength.